So can you guys please confirm that the live stream is working?
Okay, sir. Wait, sir. Wait, sir. I'm checking. Yes, sir. It is. It is.
Okay, okay, thanks.
Yeah, it's live on YouTube.
Okay, thanks. Give me a moment. I will start screen sharing and then we'll do it. Right. You are right. Are you able to see my screen?
Yes, sir.
Okay. So we'll first begin with this week 3, okay? All right. So I'll quickly go through the contents. Okay, you can stop me at any point where you have doubts. Okay, and then we can go over it like in detail. Okay. So there are like two options, right? Right. So the first option is that we have some very small crisp notes, okay, or else so we can go through that, or else we can go through the normal lecture slides, like each lecture slides, and then we can go through the each content in detail. So how do you want it?
So let's start with this one, and then we'll see if there are any specific doubts with the lectures. This sounds
Okay,
looks good
okay,
actually.
okay, fine, that's great. Okay, so the four fundamental subspaces we have this column space, the row space, the null space, and then the left null space, right? The column space is this like we'll be forming this column space using the columns. Okay, so obviously the columns they should be independent. Okay, so and then the row space will be this columns of this A transpose. Okay, so I mean there is a subspace found by this rows. Okay, A11, A12, A1, and that's one vector, right? Similarly, using the row vectors, we'll be forming this row space. Okay, so and then this null space of A is anything of the form Ax equals to 0, right? So this Ax equals 0 part. So using this vectors, suppose let's say Ax1 equals 0 is satisfied, Ax2 is equal to 0, and then Ax3 equals 0. Okay, these three are the three possible different vectors. Then the null space of A will be the span of this x1, x2, and then this x3. Okay, so these three vectors, they'll be forming the null space, and then the left null space is nothing but this A transpose x1, A transpose x1 should be equal to 0, A transpose x2 should be equal to 0, A transpose x3 should be equal to 0. So they will be forming the left null space. Okay, so those four are the four basic fundamental subspaces we have. Okay, with this we'll move forward. So the main important thing we need to be noticing is that the column space of A will be equals to the will be equals to the I mean the rank of the A, okay, will be equals to the number of I mean or the number of independent columns in column space of A, and then the row space of A. Okay, so the number it will be equal. Okay, So for suppose if the column space of two dimensional, right, then the row space will also be two dimensional, and the rank also will be equal to 2. Okay. So basically the length of the column space and then the length of the row space and then the rank of A, all those three it will be equal. Okay. Then the other important thing that we need to be noticing is the length of columns. Suppose we have this n columns, right? N columns it will be equal to the rank plus the rank of this null. I mean the length of this null space of A. Okay. So the dimension of null space of A. Okay, so this will be equal, and then M will be equals to R plus dimension of null space of A transpose. Okay, so this element will be satisfied, and again this R will be equal to the dimension of column space of A. Okay, or that will be equal to the dimension of the row space of A. Okay, or else we could write it as column space of A transpose. Okay, all right. So this it will be satisfying. Okay, now we'll move forward. Now this orthogonal vectors and this subspaces, right? Two vectors x and y are said to be orthogonal to each other when they are when the angle between them is like perpendicular. So if the angle between them is like 90-degree perpendicular, then the dot product between those two vectors it's going to be equal to 0. So basically x dot y will be 0 or y dot x will be 0. Okay, both the same. And then this x transpose y, x dot y is equal to x transpose y, right? Or similarly, y transpose x it will be equal to 0. Okay, and then the other important thing that you need to be noticing is suppose you have this u and v, if they are like orthogonal subspaces. Okay, this just contains the subspace of some vectors, right? We also contain some subspace of the vectors. Okay, so suppose let's say like x belongs to v. Okay, x belongs to u, and then this y belongs to v. Okay, for all vectors of x belongs to u, and then for all vectors y belongs to v, if x dot y is equal to 0, okay, that is the x transpose y is equal to 0, okay, then these two subspaces, they are said to be orthogonal to each other, or u comma v are said to be this orthogonal subspaces. Okay, so now using these two, okay, using this, that's u comma v are orthogonal subspaces, right? We can see here that the row space, right? Okay, the row space which is the columns of this A transpose. Okay, they will be perpendicular to the null space of the A. Okay, so the reason for that is I'll explain. Suppose we have a vector, we have a matrix A. Okay, so what is the definition for this x to be the vector of null space? Ax should be equal to 0, right? Correct. So and this A, we can be writing it as R1 row 1 row 2 row 3 row 4, right? And then this is a vector x. Okay, so this vector this is like perpendicular to this, right? So basically this R1 is perpendicular to this x, and R2 is perpendicular to x, and similarly we'll be having it for entirely. Okay, we'll be having it entirely. That is here we have this one as R1x is 0. Okay, R1x is equal to 0, and R2x equals 0, R3x equals 0. Okay, what this basically means is R1 is perpendicular to x, and R2 is perpendicular to x, R3 is perpendicular to x. Okay, R1 dot x equals 0, R2 dot x equals 0, R3 dot x equals 0. Whatever x vector you have, right? Suppose you have x1, x2, x3. Similarly, R1 x1 will be equal to 0, R2 x2 will be equal to 0. R1 x1 will be equal to 0. Okay, and then R1 x2 will be equal to 0. Okay, R1 x3 will be equal to 0. Similarly, here also R2 x2 will be equal to 0, and then R2 x3 will be equal 0. Okay, so here the u is equals to r1, r2, r3, okay, and so on, rm. Okay, so and then here v is equals to this x1, x2, x3. Okay, so for any vector in u, it is perpendicular to any vector in v, right? So as I told, if that is be satisfying, that is x dot y is equal to 0, where x belongs to u and y belongs to v, u comma v are orthogonal subspaces. So here basically this row space is perpendicular to this this null space. Okay, so basically those two are the orthogonal subspaces. Okay, the rank of A, this row space of A is this. It will be represented by R of A, right? R of A is perpendicular to this null space of A. Okay, and similarly we have this column space of A. It is perpendicular to the opposite, that is the A transpose y equals 0. Because in A transpose y, suppose if we have A transpose y, right, is equal to 0, then what do we have? We have here, this is C1. Okay, the columns will become the rows. Okay, and the same thing, this y, it will be equal to 0. Okay, so C1y is equal to 0, C1 dot y is equal to 0, and C2 dot y is equal to 0. Okay, C3 dot y is equal to 0, and so on. So basically, the column space will be perpendicular to this left null space. Okay, A transpose y equals 0. Okay, is this clear?
Yes, sir.
Okay, yeah, and this dimension of column space of this A transpose, and then this dimension of this null space of A transpose. Okay, this I have already discussed, so that part I guess is okay. Okay, later we will move on to this projections. Okay, so generally we have two cases. Okay, so two vectors can be like parallel to each other, and then they can be perpendicular to each other, but those are just the two extremes, right? They can be a vector, okay, which is neither perpendicular or nor like entirely parallel. Okay, so in this particular case, like here, right, this b vector, okay, it is not perpendicular to a vector, and neither it is like parallel to a vector. Okay, so in this particular case, there is going to be a projection of b. Okay, there is going to be a projection of b onto a. Okay, onto a, and then there is going to be some projection which is also perpendicular to a. Okay, that is called as error. The perpendicular component, that is called as error. Okay, e which is this projected, the actual error minus this projected value p. Okay, b minus p. Okay. So this projected vector, okay, this projected vector, you'll be getting it by A transpose B, okay, divided by A transpose PA by A transpose A. Okay, or else this can be rewritten as A transpose by A transpose A B. Okay, where this A transpose by A transpose A, it is called as a projection matrix. Okay, projection matrix of A. All right. So once you know this projection matrix, right? If you know projection matrix, then you can find any vector projection onto this matrix. Okay, or this vector A. Okay, in this particular case, if you want to find the projection of B onto this vector A, right, it will be equals to A transpose by A transpose A multiplied by B. Okay, suppose if you want to find the projection of some other vector C onto A, then it's going to be A transpose by A transpose A multiplied by C. Okay, so basically you can just directly multiply with that particular vector, and then you can get the projection matrix. Sorry, the projected vector using this projection matrix. All right, is this okay? What I'm
Sir,
talking
why
about?
why the perpendicular component is called error? Is just the nomenclature, or there is some rationale behind it?
What, can you repeat?
Why the perpendicular component is called as error? Is this just the nomenclature, or there is some rationale behind it?
Okay, so see, it's not like the nomenclature or like something. It's just see, we want to project this vector onto this, right? See, it has two components. Okay, it has this projected component and then this perpendicular component. we are interested in the projection component, right? So this is our major part, and whatever part is left out, that will be like unknown. I mean, unrequired part. So that is why it's called as this error. Okay. This
Okay.
b will be equal to the projection plus error. Okay. So basically, that extra part other than the projection, that is called as error. That's it. Okay. Okay. We'll move forward.
Okay.
Now we have this x equals to b case. Okay, so not all will be having this x equals to b. It will not every time it will be having a solution. Okay, because if b does not belongs to the column space of a, right, then this will not be having a solution. Okay, so in this particular case, what are we going to do? Okay, in this particular case, what are we going to do? We are going to find x. Okay, we need to find a vector x such that this ax and b, right, the difference between the ax and b, the error, that's going to be the minimum. Okay, so how do you do it? You can be getting it by using this formula. Okay. Okay. So this error b minus ax, right? Ax is the projected vector, and then this b is the actual value. This error we cannot be getting down to 0 always. Okay. So the way for you to minimize it is you can be using this one. A transpose Ax equals to A transpose B. Okay. If you solve for this, I mean, using this, you can be getting this x value. Okay, the x vector. All right. So this is the least square ones. Okay. So this is the entire part of this week 3. Okay. So this is the concepts in the week 3. Okay. If you have any doubts, we can discuss.
No, sir, no. So you will also solve the question related to these topics now, or give us some questions.
Yeah.
Okay.
Okay. So we'll not be solving all the problems, okay, but we'll be solving the problems which are like important, okay?
Okay, sir. Okay.
Okay.
So, okay.
Yeah. So for this particular one, right? Okay. Now we have this matrix A, okay? For this, they asking us to find all the fundamental spaces, okay, the column space, the row space, and all, okay? Now, if you could see here, yeah, we have 1 2 1, okay, and then this 4 8 1 2 minus 1, and then this 4 8 minus 4, right? This 1 2 1 multiplied by 4 is nothing but this 4 8 minus 4, correct? And then
Yes.
this 1 2 minus 1 multiplied by 2 is nothing but this 2 4 minus 2. So basically, the column space of A will be equals to only one vector. Okay, because these three vectors are similar. 1 2 minus 1. Okay. Similarly, the row space, right, is 1 4 2 multiplied by 2 will be equal to this 2 8 4 multiplied by minus 1 will result in this third row. So the row space of A will be equal to the span of 1 4 2. Okay, is that clear?
Yes, sir.
Okay, so now that we have here the number of columns for this is equal to 3, right? But then the dimension of the column space of A is equals to 1. So what should be the dimension of null space of A? It should be equals to 3 minus 1, 2, right? So basically, you'll be getting three vectors. So I mean, two vectors. Okay, so the dimension for this null space of A, it's going to be equals to 2. Okay, you can just solve for this. You can take this Ax equals to 0. Okay, and then you can be getting the solutions for it. Okay. Similarly, for left null space, right? Since the rank is equals to 1, okay, even the left null space also, it's going to be equals to the dimension for that, it's going to be equals to 2. Okay, and we know that the dimension of column space of A is equals to the dimension of row space of A is equals to the rank. Okay, is that clear? I haven't solved for this null space, but then you can be solving that easily using this Gaussian elimination. Okay,
Okay, sir.
clear? Yeah.
So null space is, you mean null space is nothing but I mean left null space nothing but a transpose null space, right?
Left null space you're talking about?
Yes, sir. Left null space.
Left null space is the solutions for A transpose X equals 0. Yeah.
Okay. Okay. We just need to transpose the matrix only, right?
Yeah. You just need to transpose the matrix and then find the vectors x such that A transpose x equals 0.
Yeah, solution like. Okay, all right, sir. Thank you.
And so for column spacer, we have to reduce that matrix to the RREF, na?
Can you repeat?
Yeah. He wants like we have to reduce that matrix to the row reduced echelon form, right?
Yeah.
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 Okay.
So
For both.
yeah, and for the pivot vectors, we have to identify those columns, right? The column space,
The pivot vectors, they will be giving you the column space. Yeah.
column space.
And then if you do the same for row A transpose, right, then you'll be getting the row
Row is
space.
Okay, sir.
Okay.
Got it. Yeah.
Okay. So we can be solving for this Ax equals to B also. Okay. In this particular case, the same thing was given. Okay. A was given. Okay. 1302, 0014, and then 1316. Okay. Based on the B value, we can be using this Gaussian reduction. Okay, method. Okay. So here the equations which we got is this one by doing this Gaussian elimination one. Okay. By uh, by getting it to the upper triangular form, right? What we got is we got this 0 0 0 0 the bottom row. Okay. B3, this should be equals to the B3 minus B1 minus B2, right? So basically the B3 minus B1 B2 minus B2, that should be equal to 0. Okay. So that's the one condition, and then the second condition will be equals to this this x2, right? So yeah. So x3 plus x4 or 4x4, that should be equals to b2. Okay, and then similarly the x1 plus 3x2 plus 2x4, that should be equals to b1. So based on that we should be getting the solutions for that. Okay, is this clear? This we will be getting multiple solutions here. Okay, because the unknowns are 4. Okay, the unknowns are 4, but then the equations are only 3. Okay, and even in that equations we got this we got only this one entirely became like zeros, right? So even there we did not get like entirely. Okay, we got only like 3 equations and then 4 unknowns, so we'll be getting multiple solutions here. Okay, here, and then the other important part that you need to be noticing is you'll be getting a multiple solutions. Okay, when the when n is not is equals to the rank. Okay, if n is not equals to the rank, then Ax equals to B, it will be having the multiple solutions because Ax equals to 0 has some solutions. Okay, let me just explain it.
So basically, when we have more for variables than the
Yeah, suppose let's say like you have this x1. In those we have this four unknowns, right? 4 unknowns and then 3 equations. So basically there will be having multiple solutions. The reason why you'll be having multiple solutions is there in that particular case you'll be having some vectors x1 such that x1 equals 0. Okay, and then let's say like you found a vector x2 such that ax2 equals to b, right? Then any vector of the form, okay, x2 plus alpha x1, right? A into x2 plus alpha x1, this will also be equals to b because ax2 plus alpha into ax1, this part will become 0, right? So you'll be having multiple solutions. You'll not just be having one vector solution. Okay, you'll be having multiple solutions. Okay, is that clear?
Would you slow down a little bit and then say this again? Not just this part, from the matrices which you were showing.
From the
A few minutes back, you were on the slide, right? You were on the slide which was showing some content where you.
yeah. That's fine.
Can you just a little bit slow, please?
Okay. So,
Sorry to be asking at the end, but I just wanted to understand better.
yeah, that's totally okay. So here we got up the form like upper triangular form, right? So from the bottom, what do we get? We should be having this condition of B3 minus B3 minus B1 minus B2, that should be equal to 0.
Yeah.
Okay. So here we can be getting a solution. Okay, we can be getting a solution only if this is only when this will be holding true. Okay.
Okay.
So this is the person that should be holding true. Okay, and then the second thing also for the other parts, here you should be getting a vector, right? You should be getting a vector x such that it should be equal to the b1, b2, b3. So that vector will be x1, x2, x3, x4, right? I mean, basically it has this four unknowns, right?
Correct.
Because you have four columns.
Yeah.
Okay.
3 by 4.
You have four unknowns, but then you have only three equations here. So basically, you'll be having infinite. I mean, you'll be having many solution. You'll not just be having a unique solution.
Correct.
So that's what I was trying to emphasize. And then the other way you can say that it will be having a multiple solutions is here the n is equals to 4, correct?
Mm-hmm.
N is equals to 4, but then the rank will not be equals to 4 because it is a 3 cross 4 matrix. The rank will at max be equals to 3.
Yeah.
Am I clear on this?
Yeah, you are clear. But here in this case, the rank is only 2, correct?
Yeah, the rank is only 2.
Okay.
But we even without going for this, we can say that it will be having a multiple solutions. I'm saying.
So, okay, whenever we say A is 4 by 3 and we have only 3 equations, that's anyway, we are saying it is not solvable, correct?
Yeah.
No, it's solvable. It will have multiple, it will have infinite solutions.
Yeah. It will be having multiple solutions as well. Okay?
Okay.
Yeah.
So I think generally, if m into n matrix, if the rank is n, then you'll have a unique solution. If rank is less than n, then nullity will be something, which means you'll have multiple solutions.
Okay. Yeah. So generally, we can just say that based on nullity. Okay. The dimension of this, if the dimension of null space of A, if it is not equal to 0, then it will not be having a unique solution. Okay. Then it can have multiple solutions. Okay.
Yeah. In this, in this case, we have 3 equations, 4 variables, and if the rank is 3, I still will not find a solution, correct?
You
4
will
variables.
find solution, but then you'll be finding what multiple solutions. Yeah, you'll not be finding unique solution, even if the rank is 3.
Yeah.
Okay.
Okay. Got it.
Now here we are asked to find the projection matrix for A. This is just a computation one. Okay, we just need to do this A transpose by A transpose A. Okay. So this I will not be doing this. Okay. This I hope you can do it. Okay. So once you find this A transpose by A transpose A, right? Later for you to find the projection of B onto A, all you need to do is you need to do this P star B, that is A transpose by A transpose A multiplied by B. Okay. Here I want to emphasize on one thing: projection of B onto A and then projection of A onto B, both are different. Okay. Projection of B onto A will be equals to the A transpose by A transpose A multiplied by B. Projection of A onto B, okay, projection of A onto B, then that will be the opposite. That is BB transpose by B transpose B multiplied by A. Okay. Is the difference clear?
Okay, sir.
Yes,
Yeah.
sir.
See, the difference will be because you see here this is B, okay, and then this is suppose A. Okay. Then this will be the projection of B onto A. Okay, but summarize for 90 degree. But this is the projection of A onto B.
Okay, sir. Understood. Yeah.
Okay, so
Yeah.
both the vectors they will not be same.
Okay.
Okay, all right. Now in this particular case, we were given A, okay, and then we were given B, okay. So we were not able to get the exact solution. Okay, so what we want to do is we want to find x. Okay, that will be minimizing it. So the way you need to do it is you need to do this A transpose A. X should be equal to A transpose B. Okay, we can get the A transpose from this A, and then we can multiply A transpose A. From there, what we got is we got 55, 15, 15, 5. Okay, so this x that I can be just be representing it as like this theta 1, theta double h, or you can just write it as m and c also. Okay, so this will be equals to, it should be equal to this A transpose B. Okay, A transpose B that was found as 49, 14. Okay, so basically by solving what we got is we got this theta dash as 0.7 and theta double h also as 0.7. Okay, so which basically will give you the solution for this is y equals to 0.7x plus 0.7. Okay, the ultimate value which you're getting, right, this theta dash and then this theta double dash. Okay, the solution, the vector that will give you this constants m and c. Okay, that will give you constants m and c. So but this you need not worry about. You just need to worry about this vector. Okay, that vector you can just be finding it out by doing this one. Okay, A transpose Ax equals to A transpose B. By doing this, you can find out the solution for it. Okay, is this clear? The least squares one.
Okay, so in the numerical or in the question we have it is given 8 and B, na?
Yeah. It will be given A and B.
Okay,
So
okay.
basically, you should be finding a vector x such that the array will be minimum.
Okay, sir. Okay.
So
Polynomial also can be asked like in the previous
What?
maths 2 we had polynomial also. Is that a possibility?
yeah, the polynomial possibility will be there. Okay, see for the polynomial to be there, we should be having what multiple. See, here we just have what the vector is of like R2, right?
Correct.
The vector is R2. Okay, if you have vector of R3,
R3.
R4, then you'll be having a polynomial.
Okay.
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 And so if we have polynomial, then it is better to reduce that thing to the reduced form, row echelon form, and then calculate the x1, x2, and x3.
See, you need not have. Yeah. There it is better to do it in that way. Yes, correct.
Yeah, no? Okay.
Because you'll be having a bigger matrix here, right?
Ha,
So
ha, ha.
yeah, you can go by that way.
Okay.
Right. Okay. So that's all we have from week 3. Okay, if this is clear, then we'll move on to week 4.
Yeah, sir, clear, sir. This is clear. Oh,
Okay. So now we'll move on to this week 4. Give me 1 second.
sir, you will upload these notes and all the things to the portal now?
Yes. We'll be uploading.
Okay.
One second. Are you able to see the screen?
Yes.
Okay. Now we'll just look into the slides itself. Okay, so this way we can be so in the week 4, right, we have looked into this linear regression part. Okay, so here what we do here, this x1 y1, right? So this x1 is a vector, x1 is this input parameter, and then this y1 is the output value. Okay, so we should be finding a weight such that x1 theta, x1 transpose, I mean x1 dot theta, that should be equals to y1. Okay, but like always, we cannot be finding the exact value that will be equals to the y. Okay, so this just like in the previous week we were discussing about this ax equals to b, right? So consider this a as this a as the a as this rows. Okay, I mean a as the sum of this x1 x2, this what is it, the combination of this x1 x2 x3 and so on, this xn. Okay, so this b will be equals to y1 y2 y3 and so on yn. Okay, we can't be finding x, okay, such that ax equals to y will give you the exact solution. So what do? We want to minimize the error. Okay, we want to minimize this error. Okay, if you take the theta, okay, theta as that xi transpose theta, that is this the dot product of this x1 on this theta, okay, minus y1, this is a predicted value, and then this ya is the actual value. The difference between those two, it should be as minimum as possible. Okay, so our goal is to minimize this error. Okay, so for you to minimize it, we use that a transpose a x equals to the a transpose y thing. Okay, so here let's find it how we'll be doing it. Okay, so as I told, we have this this x1, x1, x2, and so on this xn. If you form that as rows, then you'll be getting this A, which is this future matrix. Okay, this y is the values, y is the actual values. Okay, so this xi transpose, x1 transpose theta, those are the predicted values by your ML algorithm, by your ML linear algorithm. Okay, this a theta minus phi, that is this error. Okay, so this xi is xi transpose theta, okay, minus phi whole square, right? That can be rewritten as this a theta minus phi transpose multiplied by a theta minus phi, right? Because this is nothing but this is nothing but the length of this particular vector, right? The sum of this I equals to 1 to n. It is nothing but the square of the length of this particular vector. So we know that the square of length of the vector is equals to the x transpose x. In this particular case, x is equals to a theta minus phi. So a theta minus phi transpose a theta minus phi, that's going to be equal to this value. Okay. So now we need to be minimizing it. Okay. So we need to be minimizing it. So in order to minimize it, the differentiation value, the whatever differentiation you do, that should be equal to 0. Okay. So if you do the differentiation part, you'll be getting the same thing like we got before. If you remember, we had there a transpose a x equals to a transpose b, right? In place of x, I told we are using it as theta, and then in place of y in place of b we had the y. So basically we got the same solution. A transpose a theta is equals to a transpose y. Okay. So by doing the inverse of it, theta equals to, you can find this weight vector or this the solution for this linear regression, a transpose a inverse a transpose y. Okay.
Sir, I have a question, sir. L of theta, the error.
Yeah.
Sir, the L of theta, sir, it is half. It is half of this a theta minus y transpose and a theta minus y. And so in the above formula, the L theta is half of summation of
This
this term up to n.
Okay, this half is just taken to eliminate this value. That is this. You need not worry about this half part. Okay, so this half is taken so that when you're doing the differentiation part, that 2 will get cancelled out. Okay.
Okay.
You need not worry about that.
No,
Okay.
sir, I thought the usually error we have the formula error is the
Error is equal to this one only.
what, sir?
This one only. The xi theta minus y whole square.
Sir, I know that's okay. But sir, my question is that error is okay, the actual value and the predicted value. We sum
Mhm.
all and we divide by the number of observations. So there
Yeah.
is no 1 by n here.
Yeah. I mean, here we did not take n because we are not looking for the mean error, right? We just want to minimize the overall error. The sum error, if you're minimizing the mean error or if you're minimizing the overall error, that's the same, right?
Okay, got it.
Here the n is same. So basically, if you want to minimize the mean error, it's just the same as the since the denominator is constant here. Basically, you are just doing the same. The numerator, that is the sum of the square errors, you are minimizing it. So it's the
Okay.
same.
As we will only in the question or in the exam paper, it is not derivation something na. We only get the questions
No,
related
no,
to the formulas.
no. You'll not be asking for derivations. We cannot
No,
be asking for it. Obviously.
Only. Okay. Only
Yeah.
numericals.
one question here. When we're actually solving or finding the differentiation, doing the differentiation with respect to theta, it's a into a theta minus y, that is one term. A transpose into a theta minus 1 minus y is one term. Then there will be a plus a into or I trans a theta minus y transpose into a also should come, correct?
Okay,
The
can I repeat?
second, this is the
You,
product of
you,
these two in the brackets, right? The brackets which is having transpose and bracket which is not having a transpose. When I
okay.
differentiate this theta, I will get a transpose into a theta minus y plus a theta minus y transpose into a theta, a into a, right? That term, where has that gone?
Wait, let me just write it down. Wait, so this here we have this a theta minus y transpose multiplied by a theta minus y, right?
Why?
So here what do you get? You get 8.
A
You get
transpose into a theta,
theta transpose minus phi transpose multiplied by a theta minus phi, right?
correct.
Correct here?
Yeah,
This is going to be theta transpose a theta minus, and then you're going to get theta transpose
transpose a transpose y,
y minus y transpose
a theta.
a theta
The
plus
previous term should be theta transpose a transpose.
which one?
The second term should be theta transpose a transpose y.
Okay, theta transpose a transpose. Okay, so see this theta transpose a transpose y and y transpose a theta both are same, right? See this a theta, this you can write as a theta whole transpose y, or this y transpose a theta. Both are same, right? X transpose y and then y transpose x both are same, correct? Am I right?
Yeah, not so
Yes,
sure.
sir.
Yes, sir. Yeah, got
Theta
it.
transpose A transpose Y you have.
Yeah,
This you can write as A theta whole transpose
yeah,
multiplied
that,
by Y.
yes,
And then this Y transpose A theta. So basically this and this both the same. Correct? So this I can write as minus two Y transpose theta transpose A transpose A theta. And then this I can write as A Y transpose theta 2. Okay.
yeah,
This I can write in this way.
yeah. And y transpose is a constant. We can, y transpose y is a constant. We can leave that. That's, yeah, okay.
Yeah, okay. So yeah, that's how we got this. Yeah. Okay. 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 Now we'll move forward. This error is the smallest one. The difference between the predicted value and then this actual value, that is this error. Okay. So basically we will not be getting this exact value. So there is going to be some error. This maximum likelihood approach and all, even if you do it this way and then the other way, it's going to give you the same solution. Okay. This we are not going to get deep into it, so we'll not be discussing that here. Okay. So basically what we can understand here is this, both the ways we'll be getting the same solution. Okay. We need to be minimizing it. We need to be minimizing the same one. Okay. For the polynomial regression, okay, before what we have seen is we have seen multiple features with the with the linear regression, right? Here we be having the same feature. We'll be having a single feature, but then of a polynomial. Like of a polynomial, like we'll be taking x square, x power m. I mean x cube, and so on x power m. Okay, the same feature itself. We'll be taking it of the form like polynomial. Okay. So even if we solve it in this way, okay, it's going to be the same one, okay, except that here, before the constants of the theta which you're getting, right, they belong to the theta 1 x1 plus theta 2 x2 plus theta 3 x3 and so on. But here they belong to this theta naught plus theta 1 x plus theta 2 x square plus theta 3 x cube and so on. Okay, there where you are using this theta, right, that's where the difference, that's where the difference will be existing. Okay, am I clear on this?
Yes, sir. So I have a little confusion that earlier you said for it is polynomial, it is theta naught, theta 1x, theta 2x square. And so for the normal one, it is theta 1 x1, theta 2 x2.
Yeah, theta 1 x1 plus theta 2 x2 and so on, theta m xm. Yeah.
Okay, okay.
So both the ways you'll be getting the same exact thing. Okay. So this we need not have to worry about it. So all we need to just look at it is that we need to be solving for when you're given when you're given, right, you need to be solving for this A transpose A transpose A x equals to A transpose y. Okay, that alone, if you're able to solve, you'll be getting the x value. Okay, right.
Okay, sir. Okay.
So now we'll be looking at this eigenvectors.
Okay.
Eigenvectors for a particular matrix, right? So eigenvectors are vectors for which the direction will not be changed. That is, when you multiply the vector with that matrix, then the then you'll not be changing the angle or the you'll be only able to scalar it. That is, you can either like minimize it or like maximize it, but you won't be able to change the direction of it. Okay, that is, so if you do this ax, right, ax, okay, whatever the resultant you get, it will only be equals to the, it will only be parallel to the resultant one. That is, ax will be parallel to x itself. Okay, so the exact value will be equals to x equals to lambda x, where this lambda is called as this eigenvalue, and then this x is this eigenvector for this corresponding matrix A. Okay, so that's what I mean. Only for this. Only for the eigenvectors, the angle will not be changing, but for the others, right, the angle might change. That is, okay, suppose let's say ax1 equals to lambda 1 x1, because here x1 is eigenvector. Okay, that is the resultant vector lambda 1 x1, it is parallel to x1, right? But then let's say we have some other vector y, okay, where y is not eigenvector. Sorry, y is not eigenvector for A. Then ay will not be equals to the some lambda times y. Okay. In fact, the resultant vector, right? This will not be parallel to y. So suppose let's say this resultant vector is equal to z. Okay, y is not parallel to z. Okay, so only for the eigenvectors, only for the eigenvectors, the multiplication of the matrix with respect to the eigenvectors, it will give you the scalar multiple of that particular vector. Okay, so we know we know how to be finding this eigenvectors. Okay, so we have here this is just an alternate way of like solving for that. We have here for this x equals lambda x the same thing. By solving for this x equals lambda x, we'll be getting the solutions are a minus lambda I, right? If you the determinant of a minus lambda I, that should be equal to 0. So by equating it to 0, you'll be getting the lambda values or the eigenvalues, and using the eigenvalues, we can solve for the eigenvectors. Okay.
Okay, sir.
So I, as I told you, for a matrix A, and then if lambda is eigenvalue and the x is eigenvector, then ax right, the ax it will be in the same direction. Okay, that is the resultant ax, it will be parallel to x. Okay, if it is not, if x is not a eigenvector, then ax will not be parallel to x.
Age matrix.
Yeah, A is a matrix. Okay.
Can you repeat the
Or
last part
else in
again?
other parts,
If
yeah.
it's not an eigenvector, it will not be parallel to the other. Sorry, that part when you.
Okay. Here I told you that ay where y is not eigenvector, right?
Yeah.
Then ay will not be parallel to ay is not parallel to y. Okay, ay is not parallel to y.
Okay.
Okay. So or else in other words, right, we can be saying that this x lies in this. Okay, x lies in this projection matrix. Okay, this the projection, right, the projection of this whatever we have this ax, right, okay, ax that will be giving this projection matrix, no? So this x will be lying in this projection matrix itself. Okay, so for a projection matrix, for a projection matrix, right, we will be having lambda equals to 1 because px equals to xx. That's the only thing that can happen. That is, see, the maximum value for a projection matrix, px, okay, it should be parallel to x. Okay, and then the other way is it should be equal to lambda x. Okay, so the only way the length of this, I mean, or in other words, this p value, right, this p matrix value, that's going to be equals to the length of the each vector in this p, that's going to be equals to 1. So this mod of px, okay, if it is equals to lambda x, then the lambda value, it should definitely be equals to 1. Okay, that is, we have this vector b, right? Okay, and then if you have this, if p projection onto x, if it is equals to lambda times x, okay, that which basically means this px is already parallel to, let's say this is b. Okay, this is b. Okay, I'm projecting b onto a. Okay, that's what we have seen, right? That's what we have done until now. Okay, if the projection of b is parallel to a, what does that say? B is already in the direction, in the same direction, right? B is already in the same direction as a. Okay, and then what will be the projection of b onto a? If b is in the same direction, then the projection will be equal to b itself, right? Because the angle is here 0. So that is the reason we will be having, since the px equals to b here, or px equals to x here, the lambda will be equals to 1 here. Okay, is that clear what I was trying to say?
Um,
Uh, yes, sorry, Ravi. Yeah, continue, Ravi.
go on, please. Go on.
This,
Sir,
yeah.
yeah, I was asking that you said that mod of px should be equal to mod of lambda x, right?
Yeah,
When
mod
you're
of px will be equals to mod of px should be equals to mod of lambda x.
so when you're saying that mod of px, it means that its direction may change, right?
See,
It may
mod
come
of
in
px,
180-degree, right? So even if it is coming in 180-degree, there is a change in direction, right?
see, the projection of px onto this can be equals to, yeah, then the projection is going to be this one. Yeah, it can be equals to -1. Check here. Yeah, actually, yes, it can be equals to -1. But then if they're like exactly parallel, okay, if they're anti-parallel, then it will be equals to -1. If they're exactly parallel, then it will be equals to 1. Okay.
So if it is anti-parallel, so its direction is changing now. So the phrase
Yeah,
which we are
yeah, yeah.
using,
Then yes.
the the phrase which we are using, that should not change
Okay,
the
wait.
direction. That
Even in that particular case, right? Let's say like the you're talking about A is in this direction, okay?
correct.
Then this B is in this direction, correct?
Right, right. So this is
Then
180 degree.
what is
Yes.
going to be a projection of A onto B? It's going to be B itself, right? It's going to be B itself. Okay.
Hmm.
So now we have here projection of P, okay? Projection of P onto B, it will be equal to B itself, okay? Even though A is like exactly anti-parallel to B, okay, A is exactly anti-parallel to B. The projection of P onto the projection of B onto A, it's going to be equal to B itself, which will give you lambda as 1. Okay, that parallel or anti-parallel, that will be taken care in the B itself. Okay.
Okay. No, my point is that the phrase which we are using, that the original vector should not change its direction, right? So here it is changing its direction. That is
Yeah,
my
yeah,
point.
yeah. So when for a projection matrix, right? For a projection matrix, to have an eigenvector, that vector it should be parallel to this parallel to the yeah parallel to a projection matrix. Yes, correct. So and then the only way that can happen is when the lambda value it will be equals to 1.
One or minus plus one or minus one, right?
No, it's going to be 1 only. As I told you, PB it will be equals to B. Okay, this direction it will be taken care in the B itself. Okay, whether it is exactly parallel or anti-parallel, that will be taken care in the B itself. Okay,
Okay.
now making
But
sense
I
here?
have a different question here on the same thing. When PB is equal to B, then P's projection matrix itself is unity, right?
Can I repeat?
If PB is equal to B,
Yeah,
then P is equal to 1, isn't it? Or vector 1, which is unity, or
PB is equals to B, then
P is equal to 1, correct?
P. What's P?
Projection matrix is equal to 1.
No. The projection matrix is not equals to 1. Projection matrix need not be equals to 1. Right?
What?
It's a matrix, right?
Will it be
It's a
identity
matrix.
matrix?
P is a matrix. P is a projection matrix.
Is it an orthonormal matrix, or under what circumstance would PB be equal to B?
If P is identity matrix.
P is going to be equals to this A
Exactly.
transpose by A transpose.
That is what I
B.
mean to say by unity. It's identity matrix. Sorry, my
Yeah, it's a
use of
symmetric matrix. It's a symmetric matrix. That alone we can say. Okay. Is this clear now? Still confusing?
No, it's not. It's not about the projection matrix definition itself, the way you derived it a little earlier. In the case where we are multiplying a projection matrix into another vector and then get the same vector, that means the projection matrix is a identity matrix, correct?
No. See just because we have ax equals to x, that does not mean that A is identity matrix, right? Of course, for ix will be equals to x, but then every time we have ax equals to x, that does not mean that A is identity matrix, right? There can be matrices, okay, which is not identity, but still it will give you ax equals to x.
Okay.
Okay, we can have the eigenvalues as 1, right?
Yeah.
For a particular vector matrix.
Yeah.
So in that particular case, obviously x will be equals to x without A
Okay.
being the identity matrix, right?
Right.
Okay.
Okay.
So for this permutation matrix, which is this shuffling of shuffling of the rows of this identity matrix, no, then we'll be having this x as this 1 1. Then we'll be having this bx equals to -x. The lambda value it will be equals to -1. Okay, for the permutation matrix, the lambda value it will be equals to either 1 or minus 1. Okay, clear? But am I clear on this? For identity matrix, the lambda value or the eigenvalue it's always going to be equals to 1. Okay, but for a permutation matrix where you are shuffling the rows, okay, or shuffling the columns, either way it's the same, the eigenvalues will either be 1 or minus 1. Okay,
Okay, sir. Okay.
Okay.
the finding the eigenvalues, we can be finding it by using the determinant a minus lambda a equals 0. Okay, using the polynomial equation we can find the lambda values, and using the lambda values we can find the we can find the vector x such that by using here we have this a minus lambda I into x is equals to 0, right? So if you know lambda, then we'll be getting a minus lambda I one matrix we'll be getting, right? This matrix multiplied by x equals 0. Okay, so we know how to find solutions for this, right? We know how to find solutions for x equals 0, the nullity one. So using the same way we can find the solution for this eigenvector x. Okay, am I clear on this? How to find eigenvector? That's okay, right? That's easy, right?
Yes, sir. Yes, sir. Yes,
Yeah.
yes.
Okay. This one, the symmetric matrix, it will be having the real eigenvalues. That was like true for us here, and even for us in the Hermitian matrix, we know that the symmetric matrix will have the real eigenvalues. Okay. And then a 2 cross 2 matrix where we do not get two independent eigenvectors. The eigenvectors, when we mean by independent eigenvectors, what we are saying is the dot product between those two, right? It should be equals to equals to 0. Okay, if two vectors are like independent, then the dot product should between those two, it should be equal to 0. Okay, but it's not always that you'll be getting for two distinct eigenvalues. You may not always get independent eigenvectors. Okay, or orthogonal eigenvectors. All right. But for the case of symmetric matrix, okay, you'll be getting for distinct eigenvalues, you'll be getting a orthogonal eigenvectors. Okay. All right. We'll look into this. Matrix A is diagonalizable when we have this S inverse A is equals to this diagonal matrix. Okay. And for the symmetric matrix, we can be getting this eigenvalues. Okay, so any matrix, right? Any square matrix, okay, that is diagonalizable. Okay, any square matrix that is diagonalizable. Even when it's not symmetric, also it is diagonalizable, but only for a symmetric matrix it is orthogonally diagonalizable. And I mean by orthogonal diagonalizable is you'll not be getting S inverse AS, but then you'll be getting something like S transpose AS. Okay, S transpose AS equals to diagonal matrix you'll be getting. Okay, this part the diagonalization of symmetric matrices, that's known for you, right? Clear on this?
Sir, can you come again this? You said that diagonalizable S inverse AS and S transpose AS.
So a matrix A is diagonalizable if there exists a matrix S such that S inverse A is equals to diagonal matrix. Okay. What I'm saying is, if A is n cross n matrix, which is a square matrix, okay, with n linearly independent eigenvectors. When I mean by independent eigenvectors, previously I told that they should be perpendicular, right? They need not be perpendicular. Okay, they can just be something like, if you have here x1, c1 x1, c2 x2, c3 x3, and so on, cn xn. Okay, for it to be equal to 0, Okay, for it to be equal 0,
Mhm.
C1 should be equal 0, C2 should be equal 0, and so on. Cn should be equal 0. Okay, only when this thing holds, then you will be getting, then you will be able to, equate this to 0. Or in other words, any vector cannot be written in the written as the linear combination of the other vectors. Okay, so here if you're able to get this equal to 0, only when all of the constants are equal to 0, then we can say x1, x2, and so on xn, they form a linearly independent set. Okay,
Okay, sir. Okay.
so when a matrix, when a matrix has n linearly independent eigenvectors, okay, then it is diagonalizable. Okay, suppose you have this vectors s equals to x1 to xn. Okay, x1 to sn, because they are like linearly independent, right? Because all the eigenvectors are linearly independent, then the rank of s, it will be equals to n. Okay, if you remember the column space of A, it is equals to the number of independent columns, right? Independent columns in the matrix. So here all the n columns, they are linearly independent. So the column space of A, the column space of S, it will be equals to n. When the column space of S equals to n, then that means the rank of S is also equals to n. When rank is equals to n, we know that it is invertible, right? Uh, is it clear?
Sir, when rank equals n,
Then the matrix is invertible.
yes, right, right.
Okay. So in this particular case, since we have all the n vectors are linearly independent, okay, so this S is invertible. Okay. Now if you do this AS, okay, AX1 and all, so what you're going to get is you're going to get AX1, okay, AX1, AX2, AX3, and so on, this AXN. Okay, this AX1, it's equals to lambda 1 x1, right? And AX2 is equals to lambda 2 x2, and so on, AXN equals to lambda n xn. So this can be rewritten as x1 to xn, okay, multiplied by this diagonal matrix, where the diagonal elements are lambda 1 to lambda n. Okay, so basically A is equals to S lambda, or S inverse A is equals to this diagonal matrix. Okay, is this clear?
Yes, sir. It is clear, sir. But okay. In few minutes you will also give the example of this one now, because if you have a numerical or it's something that it will help clearly to understand.
No, for this week 4 we'll not be looking at the numericals, but
Okay, okay, okay.
see the way you can think of it is, okay. So we know that, let's say, like if the n cross n matrix, it has n linearly independent eigenvectors. Okay, if it has linearly independent eigenvectors, then the matrix you form using S, okay, that's going to be invertible. Okay,
Okay.
because the rank of it's going to be equals to n. Okay, and then we did this AS. Okay, AS is nothing but this AX1 is lambda 1 x1.
Mhm.
Similarly, AXN is lambda n xn, and this can be rewritten as this x1 to xn A multiplied by this diagonal matrix. Okay, so which is nothing but this x1 to xn is nothing but S, right? This eigenvectors matrix S multiplied by this diagonal matrix. So A is equal to this S lambda, and then you can rewrite that as S inverse A is equals to lambda. Okay,
Mhm.
but in the case of symmetric matrices, okay, in the case of symmetric matrices, what you're going to get is, okay, in the case of symmetric matrices, this vectors, or you could say this, the matrix which you got by this which you got by this eigenvectors, that's going to be orthogonal. Okay, that's not just going to be the linearly independent, okay, it's going to be orthogonal. For orthogonal matrix, S inverse is going to be equals to S transpose. So you are going to get S transpose A is equals to this lambda. Instead of S inverse, you are going to get S transpose A is equals to lambda, which is so just for a specific case of symmetric matrices, you will not just say it's diagonalizable, you will say it's orthogonally diagonalizable. Okay? We'll talk about this diagonalization of symmetric matrices in a bit. Okay? Okay.
I say it will from this part. It will only the theoretical question will come, or the numerical portion also will cover in
The
the exam.
numerical questions mostly, the numerical questions only will be getting mostly, but theoretical you can be getting slightly like the rank of orthogonal matrix, something like that will be getting. Okay, or I told you that rank of A plus dimension of nullity, null space of A,
Uh-huh.
that's going to be equals to n.
Uh-huh.
Using that, you'll be getting few problems. Okay,
Okay.
nothing as deep as this. Okay, you
Okay.
will not be asking you like A is equals to S inverse S lambda, something like that. Will not be asking. Okay,
Okay.
okay. So when we have n distinct eigenvalues, then the eigenvectors are going to be independent, okay, linearly independent. Okay. Okay. So for a matrix A to be diagonalizable, it should be having distinct eigenvalues. Okay. Previously we told that it should be having distinct eigenvectors, and now that we have established for distinct eigenvalues, you'll be getting distinct eigenvectors. Okay. So for a matrix A to be diagonalizable, it should be having distinct eigenvectors. Okay. Clear?
No, both means a distinct
Yes, yes, sir.
eigenvector as well as distinct eigenvalues, right?
Can you repeat?
Both like distinct eigenvectors as well as distinct eigenvalues.
Yeah, yeah. So if it has a distinct eigenvalues, then that means it will have distinct eigenvectors. Okay.
Okay.
So yes. Okay. All right. Not all matrices are diagonalizable. In this particular case, if it does not have the linearly independent eigenvectors, right, then obviously it's not going to be diagonalizable. Okay. Clear? And then this is the other part. Okay, it's not entirely required, but you can just note it down. This S inverse AK S, it's going to be equal to lambda power k. Okay. The eigenvalues of A power k, it's going to be equal to the power of the, I mean, that much power of the eigenvalue of the A, right? That is the eigenvalues of A power k, it's going to be equal to the lambda power k, right? So using the same thing, S inverse A power ks, it's going to be equal to this matrix, this diagonal matrix power k. Okay, clear?
Um,
Okay.
yes, sir.
So the solving Fibonacci series, we'll not be looking into it because that is just a specific use case of it. Okay, and we'll not be asking questions on it. So we'll directly move on to this orthogonal diagonalization. Okay. So for orthogonal diagonalization, okay, so what happens is, as I told you, this a matrix A can be diagonalizable, right? If it has a distinct eigenvalues. Okay. If it has a distinct eigenvalues, then this S inverse AS, it's going to be equal to this diagonal matrix. Okay. But for the case of symmetric matrix, what's going to happen is this Q inverse, it's going to be equal to the Q transpose itself. Okay. Or okay, I'll explain that in a bit. Okay. Okay, fine. So the eigenvectors corresponding to different eigenvectors are linearly independent, okay, and they are also orthogonal. Okay, the eigenvectors corresponding to different eigenvalues in a symmetric matrix, they are going to be orthogonal. So what does that say? Suppose we have here ax1 equals to lambda 1 x1, okay, and ax2 equals to lambda 2 x2, okay, where A is a symmetric matrix, so then x1 dot x2 it will be equal to 0, okay, x1 dot x2 it will be equal to 0. Now when x1 dot x2 equals 0, similarly if you form a vectors, if you form a matrix using that is x1, x2, x3 and so on xn, okay, so each of these vectors they are going to be perpendicular to each other, okay, that is xi dot xj it is going to be equal to 0 when I is not equal to j, okay. Is this okay?
Yes,
So
yes.
and then suppose if you get each of these vectors length as 1, that is mod x1 equals to 1, okay, so this particular matrix it is called orthogonal matrix, okay. And for this particular orthogonal matrix you can check, suppose if S is Q is a orthogonal matrix, okay,
Sir, if
then what you can
length,
check is Q transpose Q is equals to Y, okay. Q transpose Q is equals to Y or Q transpose is equals to Y, okay, either way it's same, or in other words Q inverse equals to Q transpose, okay.
Okay, sir.
So basically here generally S inverse A is equals to this lambda, right? But for the case of symmetric matrix, its S inverse is going to be equals to S transpose, okay. So that's the reason why we write Q transpose AQ is equals to this lambda. So it is going to be orthogonally diagonalizable,
Okay, sir. Okay, now understood. Yeah.
okay. Orthogonally diagonalizable because we have this we have here orthogonal matrix, okay. Clear on this?
Yes, sir. Yes, sir.
Yeah. Okay. So that's all we have from this week 4. Okay. After this, we
sir,
move
just
on.
a, sir, just a small clarification.
Yeah.
In that case, when the length of the vector is also becoming 1, right?
Yeah.
Then the matrix is becoming orthonormal, na? Because they are perpendicular to each other, they are independent to each other, right? So it
See,
means they are,
we don't specifically have this orthonormal matrix. Okay. That vector, right? Suppose we have. Okay.
So in case of
yes,
vector, we have orthonormal. In case of
yes,
matrix, we have orthogonal.
Yeah. Only for vectors. Suppose we have x1 comma x2. If they are perpendicular, right? X1 dot x2 if it is equal to 0, then we can say x1 dot x2 x1 and x2 are orthogonal, okay.
correct.
And if x1 dot x2 is equal to 0, x1 dot x equals 0 and mod
Length
x1
of x,
is
yes,
equals to mod x2 is equals to 1, then they are called orthonormal,
correct,
okay.
yes,
For vectors we have a distinction, but for a matrix, right, you don't have an orthonormal matrix, okay. Orthogonal matrix is a matrix where where each column is a orthonormal vector, okay.
okay. And the length of each vector is 1.
Yeah, since they are orthonormal vectors, the length of it is going to be equals to 1.
So that is called orthogonal matrix, right?
Yeah.
Okay,
Orthogonal
so
matrix, all the vectors are perpendicular to each other, correct?
Yes.
so the term orthonormal itself is not there for matrix, right? That's the summary.
Yeah.
That's the crux. Okay.
And so,
Yes.
so hypothetically, if it was there, then the matrix multiplication is 1 now. Hypothetically, I'm not saying it is there.
Which one you're talking about?
A matrix.
A transpose this Q transpose Q.
Yes, sir. Yeah.
That's going to be equals to I.
Okay.
It's
Yeah.
going to be
You are right.
I.
You are
I
right.
mean,
Ha,
yeah.
ha,
What you basically meant is same, but yeah, it's going to be equals to I.
ha.
I did.
Yeah. Okay. Yeah. You are right. You
Okay,
are
got
right.
it,
Actually,
sir.
that's the definition. That's a proper definition they say. But for Q transpose Q to be equals to
Orthogonal.
this should be satisfied. Okay.
Okay, okay, okay,
Got
okay.
it, sir. So the takeaway for me is that there is nothing called orthonormal matrix.
Yeah,
It is
yeah,
orthogonal only. Yeah.
yeah. Okay. Okay. So now we'll take short break and then we'll continue with this week 5. Okay.
5 and some part of 6, right? That
Yeah.
is very. And some part of 6, that is very.
Yes, yes, yes. Okay.
Okay.
Sir,
We'll take,
how many weeks we'll cover today, sir?
we'll
Up
be
to
covering
5.
3 weeks, 3 weeks, and then the part of week 6. So
So
basically,
once
3 weeks off.
so 1.5 or 1.2 it is remaining, no, right now. Two
Yeah,
weeks
yeah.
are covered or 1.2
Two
or
weeks are
1.
covered and 1.5 is remaining. Okay.
Okay, 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 okay,
Now
sir.
we'll take short break and then we'll continue.
Yeah, yeah, definitely.
Thanks. Okay, okay, so right. So let's continue. We share the screen. The screen visible?
Yes, sir.
Yes,
Yes.
it is now.
So before I just forgot to in the week 4, I just forgot to mention one thing. Most of you would already be knowing it. For a matrix to be symmetric, A transpose should be equals to A. Okay. So then only this is called a symmetric matrix. Okay. And A transpose A or A transpose, these two are always going to be symmetric, no matter what the matrix A is. Okay. All right. So
Yeah. Okay,
just
sir. Yeah. Yes, sir.
just keep that in mind. So when you look at this complex number, okay, so this complex numbers, it can have the imaginary part too, okay, a plus ib, where I is equal to the square root of -1 and a comma b are real numbers. Okay, so then this is called as this called as a complex number. Okay, the conjugate. Okay, here we will be defining extra term called conjugate of a complex number. The conjugate of a complex number, it's denoted as C. On top of it, you'll be writing a line that is called as A minus IB. Okay, we just be changing this imaginary part sign. Okay, so and then C dot C conjugate. Okay, if you multiply this A plus IB into A minus IB, this is of the form A plus B into A minus B, which will be A square minus B square, right? So C dot C multiplied by C conjugate, it's going to give you A square minus IB whole square. Okay, and this is going to give you A square plus B square, because I square is -1, -1 it will become +1, so it's going to give you A square plus B square. Okay, and the length of the complex number. Okay, another part is length of the complex number. The length of the complex number is equal to A square plus B square. Okay, and so C dot C conjugate, it will give you the length of the complex number. Okay, C dot C conjugate, it's going to give you the length of complex number. So, and then the conjugate of conjugate, that is A minus IB conjugate, it's going to be equal to A plus IB. Okay,
So it is square of the length, right? Not length.
yeah, square of the length.
Yes.
Okay. So C conjugate, it's going to be equal to C. Okay, so that's just a brief part of the complex number, and then the complex vectors, it's going to be just the component. It's going to just, instead of the real numbers, it's going to contain the complex numbers. Okay, so in this particular case x, it belongs to three-dimensional space. Okay, and then we have here 3 minus 2i minus 2 plus I minus 4 minus 3. Here, since we have these imaginary parts, it's called as this complex vector. Okay, and one other thing, all the real numbers are subset of complex numbers. Okay, right? The real numbers are also complex number where b is equal to 0. Okay, so real numbers are basically subset of the complex numbers, and real vectors are also subset of complex vectors. Okay, because in the real vectors you just have this minus 2i part, I part, you won't be having this I part. Okay, so basically the real vectors are also the subset of these complex vectors. Okay, so in this particular case, here we have this x belongs to C3 and then this y belongs to C3. Okay, the three-dimensional space. Okay, and then the addition of two vectors, it's just direct. Okay, we'll just be adding it, like in this particular case, 3 minus 2, it's going to give you 1, minus 2a plus 4a, it's going to give you plus 2a. Okay, similarly you'll be adding other complex numbers. Okay, the conjugate of it okay, the conjugate of a complex vector, it's going to be the conjugate of each and individual number in the vector. Okay, suppose we have z equals to 1 plus 2i, 3 minus 4 minus a, right? So you're going to do conjugate of 1 plus 2i, which is going to give you 1 minus 2i. The conjugate of a real number, it's going to be the same one. So 3 minus 4 minus 5i, it's going to become minus 4 plus 5i. Okay, only the imaginary part value should be changed the sign. Okay, so the inner product of two vectors, okay, this is similar to the dot product of the real vectors. Okay. The inner product of two complex vectors x dot y, it's equals to x conjugate transpose y. Okay. So what we have over here is we have x dot y is equals to x conjugate transpose y or x transpose conjugate y. Okay, both the same. Okay, and this will be belonging to the complex number. Okay, this will be equal to some complex number. Okay, this need not be a real number. Okay, but x dot x, it's going to be a real number. Okay, I mean where x is a complex vector and x dot x, it's going to be equals to x conjugate transpose multiplied by x. So, and this is going to be a real number. Okay. But
Sir, I have a question, sir. Here.
yeah.
Sir, when we multiply x and y, they are two complex numbers, x and y.
Yes.
So, sir,
X and y, they are complex vectors.
complex vectors. Sorry, complex
Yeah.
vectors x and y. So, sir, we need to multiply in a manner that we need to transpose and conjugate the first vector, na?
Yes.
And,
Yes.
okay, not the second
Transpose
one.
and conjugate or conjugate and transpose. Either way is okay.
Yeah, first vector, not the second.
Yeah.
If
Yeah.
we
The first vector.
if in the question they are asking x dot y, so we have to conjugate transpose of x. And
Yes.
if they are asking y dot x, then we have to conjugate y.
Yes.
Conjugate
Exactly.
okay.
Okay. And actually, there is a relation between x dot y and y dot x. That that I think it will be mentioned here. Yeah. So x dot y is equals to the y dot x conjugate. Okay. So, or in other words, since x transpose y, it belongs to the complex numbers, right?
Uh-huh.
So, the length of x dot y is equal to the length of y dot x, because the length of the complex number and the length of the conjugate, the length of its conjugate, both are same.
Yeah.
Okay. But even though the length is same, but the actual value of the complex number, that need not be same. Okay.
Okay.
But for x dot x, it's going to give you the real number. Okay. Okay.
Yes, sir. That understood.
Okay. In other words, how you can know that x dot x equals to the x dot x will give you the real number is by this one. X dot x is equals to the conjugate of x dot x, right? By property 1. Okay. So if a number is equal to its conjugate, if a complex number is equal to its conjugate, then that means the imaginary part is 0, right? If
Okay.
a plus ib is equals to a minus ib, then that means b is equal to 0, right? Okay.
Yeah.
Yeah. And then this x dot cy will be equals to c multiplied by x dot y. Okay. That's because x dot cy will be equals to x conjugate transpose multiplied by cy. Okay. You can bring the c outside. This will become this. Okay. But
And
cx, yeah.
what is C, sir? C
C
is
is
a real
complex
number
number.
or complex number.
C is a complex number. Okay. So cx dot y, it's going to be equal to c conjugate of x dot y. C conjugate because we need to do the cx conjugate here. Okay. That is why we'll have the conjugate over here. Okay. Cx dot y, it's going to give you c conjugate, but x dot cy, it's going to directly give you c. Okay. Now if you look at this,
So C is a complex number in both 3 and 4, correct?
if c is
No, C is a complex number in both 3 and 4. Equations,
yeah.
no, sorry, okay.
3 and 4, they will not be correct. If c is a real number, then c and 4 both will be correct. Both will be same. Sorry. Okay.
No, what I mean to ask is, in 3, x dot cy is equal to c into x dot y, correct?
Yeah.
Now, there c is a real number or a complex number is my
Complex
question.
number. Complex number. In every case, wherever we are using c, it's a complex number.
Okay. All right.
Okay.
All right.
So in this particular case, in the previous weeks and all, right, there when we talked about a constant, it's a real number, right? In this particular case, it's a complex number.
Okay.
So now if you have your cx dot cy, okay, So will it be equals to mod C extra dot A or mod C whole square?
Mod C square.
Yeah, mod C whole square, right? So this false. Okay. Okay. Now we'll be looking at the matrices. The matrices, okay, it is just like the normal matrix, but in this complex matrix, we will have the complex numbers. It will have the complex numbers as its elements. Okay. Matrix is said to be a Hermitian matrix. Okay. If A star is equals to A. Okay. So
That part is missing.
yeah, that part is missing. Okay, so give me a second. So matrix is said to be a Hermitian matrix if A star is equals to A. Okay, A star is nothing but A conjugate transpose, okay, or A transpose conjugate. Okay, this is just a simple way of denoting this conjugate transpose because we will use this conjugate transpose or transpose conjugate multiple times. Okay, so if this is true, then it is called as Hermitian matrix. Okay. Hermitian matrix is similar to the symmetric matrix. Symmetric matrix. Okay. So if you look at this A here, okay, now we can actually get some few properties from the here. If A star is equals to A, okay, which basically implies A transpose conjugate is equals to A, okay, which basically implies what is going to be this A trans. Okay, let's look at this B. Okay, Aij, okay, it should be equals to the A transpose conjugate, right? So basically, it should be equals to Aji conjugate. Am I correct in this? Ith through jth column of A should be equal to j through ith column of A transpose
Yes, sir.
conjugate.
Yes, sir. Yes.
Yes, sir.
So if I equals to j, then Aii should be equals to
Yeah, conjugate.
Ai conjugate. Okay, if this is true, then we know that Aii is a real number, right? So for a Hermitian matrix, all the diagonal elements it should be real numbers. Okay, that's the first rule, and then Aij should be conjugate of Aj, and Aj should be conjugate of Aij. Okay, so here A12 is conjugate of A21, A21 is conjugate of A12. Okay, 3 minus 3, 3 plus 3. So basically A is Hermitian. B is not Hermitian because we have here the diagonal elements, they are not real. And actually even here also Aij is not equals to Aj conjugate. C is also not Hermitian because the diagonal elements are not real. Okay. The properties of Hermitian matrices, they are same as the properties of this symmetric matrices. The eigenvalues are going to be real. Okay. For a distinct eigenvalues, the corresponding eigenvectors are going to be orthogonal. Okay. Just like we have seen for the symmetric matrices, right? Orthogonally diagonalizable, we look there where the eigenvectors corresponding to different eigenvalues, they are like orthogonal, not just independent, they are orthogonal, which means they're like perpendicular to each other. So eigenvectors are orthogonal, okay, corresponding to the distinct eigenvalues for a Hermitian matrix. So this is the problem where they just ask you to find the eigenvectors, okay. So in the first case, you got it as 1, 1 plus 1i. You got it as 0, 0. Okay, here they just found the eigenvalue corresponding to 8 ohms. Okay, so you got 1 minus I2. The other eigenvector which you find, right, that will be perpendicular to this eigenvector. Okay, since the matrix here it's a Hermitian. The matrix here it's a Hermitian matrix. Okay, remember that. Now for a unitary matrix, this unitary matrix it's similar to the orthogonal matrix. Okay, In the orthogonal matrix, we saw Q transpose Q is equals to Y. This, remember?
Yes, sir. Yes, sir.
Q transpose equals to Y or Q transpose Q equals to Y. Okay. In this particular case, in our particular case of this complex, right, the complex space, it's going to be U star U is equals to I. Okay. Instead of just the transpose, we are adding conjugate also. Okay. So U transpose conjugate U is equals to I. Okay. Or U conjugate transpose it's equals to I. Okay. So if that is true, then that's called as the unitary matrix. Okay. And one other important property for a orthogonal matrix and as well as unitary matrix, the mod lambda value it's always going to be equals to 1. Okay. The mod lambda it's always going to be equals to 1. Okay. The here also for a distinct eigenvalues, the eigenvectors are going to be orthogonal.
So
Okay.
mod lambda means the eigenvalues.
Yeah, the modulus, the absolute value of eigenvalue, it's going to be equals to 1.
Okay,
Okay.
okay, okay.
Means the eigenvalues are going to be this number, will be 1, but the eigenvectors are going to be different. Is that the case?
No, we are just saying that mod lambda it's going to be equals to 1.
Mod
We
lambda,
are
sorry,
not
okay.
saying,
Vectors
we are
plus 1.
saying mod lambda is equals to 1. We are not saying
Yeah.
eigenvalues will be equals to 1. Okay.
Okay.
But for a distinct,
So
yeah.
in this case, eigenvalues could either be 1 or -1, only two possibilities, right?
No. They can be this complex numbers also, right?
So can you give an example? The mod of lambda is 1.
Can you repeat?
So can you give an example that mod of eigenvalue is 1
Okay, so
of
let's
any
look at,
eigenvalue?
But one question, sorry, just sorry to interrupt here, but eigenvalues we already were mentioning a little earlier that in Hermitian, the eigenvalues are going to be always real. So
no,
why
the
would I?
eigenvalues for a Hermitian matrix.
Okay, this is a
Unitary
This is for
matrix.
unitary
unitary.
matrix.
Okay.
Okay. Suppose if you look at here, u cos t minus sin t cos t, right? So for this u transpose, right? That's going to give you I. Okay. So basically U is a unitary matrix, but it's not like the eigenvalues they need not be real. In this case, they could be real, but it does not always correspond to that. Okay. And moreover, in
What?
this particular case, it's not actually the it's not a unitary matrix. It's this orthogonal matrix. Okay, here it does not have this imaginary parts. Okay, so
No,
okay,
I thought unitary matrices in the complex case are a subset of Hermitian. No.
yeah, no, the unitary matrices are not subset
No,
of
in
Hermitian.
the case of complex in the case of a complex.
The orthogonal matrices are subset of unitary matrices.
Okay.
Okay, see
Okay.
we have here four important kinds of matrices, right?
Hmm.
The real world and in the complex
Complex. Yeah.
world, we have here symmetric. This
Equivalent
is
to
similar to
Hermitian. Hermitian.
Hermitian. And here we have orthogonal. This is similar to unitary.
Okay.
Okay, here
Okay.
mod lambda is equals to 1. Here mod lambda is equals to 1. Okay.
Okay.
Here we can directly say lambda is equals to plus or minus 1, but here we cannot say that.
Uh-huh. Oh, okay.
Okay.
Okay. Sorry. Yeah.
Yeah.
Got it.
And in the symmetric case, right, we can say lambda real.
Mm-hmm.
Here also lambda is real.
That's real. Okay.
In both the cases, we can say if lambda I is not equals to lambda j, then the corresponding xi dot xj is going to be equal to 0. Okay. Basically,
Okay.
they are like perpendicular, orthogonal.
Okay. Okay.
So mod of lambda means the determinant of lambda.
What?
So you are saying that therefore eigenvalues are mod of lambda is 1. So that means the determinant of the lambda values or eigenvalues are 1.
Any absolute value of
No, no,
eigenvalue.
The
absolute
absolute
value of
value of the eigenvalue is going to be equal
Absolute
to.
value. Eigenvalue are scalars. No?
It's just that absolute value is equals to 1.
So if possible, can you just show us one example of the complex eigenvalue?
Eigenvalue, yeah, mode
The
of
complex
complex eigen.
eigenvalue.
Sir, 1 by root 2 plus I 1 by root 2.
No. Let's just look at the lectures if it was discussed.
Modulus is 1, so that's why.
Even here, check that it is unitary.
I don't remember seeing complex eigenvalues being discussed in this, but
Yeah.
whenever we are talking about natural frequencies of structures and we involve damping, then complex eigenvalues come in. That I know.
Yeah. So actually, we haven't discussed that, but okay,
Yeah.
you won't actually be getting the problems also on that. But just remember that the eigenvalues can be complex also. Okay.
Yeah.
And when we are saying for that, for Hermitian matrices, the eigenvalues are always real, which basically means there is a possibility for other matrices that eigenvalues are complex, right? It is implied,
Yeah.
right?
Yep.
So the Schur's theorem is important, okay? But we won't be getting questions from this, okay? So just that any n cross n matrix, okay, it is similar to this upper triangle matrix. Okay? A is equals to ut u star. So, or in other words, you can write any matrix A, okay, any matrix A as ut u star. Okay. It should be a square matrix, okay, not it should be a square matrix. That's important. Okay, not just any matrix. Okay, or u star A u it will be equals to T upper triangle, where T is this upper triangle matrix, and then this U is the unitary matrix. Okay, so u star A is equal to T, and then for a Hermitian matrix, if A is Hermitian, then u star AU, here A is any square matrix. Okay, I'll just write that down. Here it's going to be equal to the diagonal matrix. If A is Hermitian. Okay, just like we have seen here, you remember Q transpose A Q is equals to this lambda, right? For the real space. Okay. The same thing we'll be seeing here. Okay. Here in the diagonal matrix, you'll be having the eigenvalues of A, and then this U star in the U star you'll be having the orthonormal eigenvectors of A. Okay. So this is going to be the Schur's theorem. Schur's theorem is for any n cross n matrix. Okay. And then the spectral theorem, okay, any Hermitian matrix, this is going to be this diagonal matrix, right? This is going to be for specifically for this Hermitian matrix only, okay?
So spectral theorem is a subset of Schur.
Which thing? Yeah.
Okay.
Sir, are these two theorems are important for internal exams?
No, see, the Schur's theorem is not important, but the spectral theorem is important. Okay, you should know how to decompose this. Decompose A into this based on unitary matrix on the diagonal.
Okay.
Diagonalizing. Okay, you should know how to do this.
Okay.
Okay, so in the case of symmetric matrix, we told that it is orthogonally diagonalizable, right? In this particular case, Hermitian matrix, it is unitarily diagonalizable. Okay, because we are using the unitary matrix to diagonalize it. All right.
Sir, in previous slide, sir, where properties were written in the previous slides. Yeah? So one of the property was that all the unitary matrices are not Hermitian matrix. Could you throw some
Yeah,
light on that? Yeah, property number fourth
yeah,
property.
yeah.
Yeah.
Unitary matrix need not be Hermitian matrix,
Okay.
right?
Okay.
It need not be. See here itself we could see here. Here you have what? U equals to cos t minus sin t cos t, right?
Hmm.
And then this is a U transpose equals to U? No, right?
No.
U transpose is not equals to U. So even though U is a unitary matrix, right? This U star is not equals to U. So yes, it need not be. And same even there also. All the symmetric matrices are not Hermitian matrices. And not all Hermitian matrices are unitary matrices. Okay? Clear?
And the fifth one is related to that only. There exists unitary matrix that diagonalizes a Hermitian
Yeah,
matrix.
yeah, yeah. This is related to this spectral theorem.
Hmm.
For any Hermitian matrix, there exists a unitary matrix. Okay, that diagonalizes it. This there is this unitary matrix. You use that particular one.
Okay.
Okay. Okay. So the singular value decomposition, it is a generalization of even the Schur's theorem also. Okay. So any matrix A can be diagonalizable. Okay, can be diagonalized as okay Q1 A equals to Q1 sigma Q2 transpose. Okay, where Q1 is this it is a matrix that contains the eigenvectors of A transpose. Okay, and Q2 is a matrix that contains the eigenvectors of A transpose A. Okay,
So here AAT and ATA are different.
what?
Here AAT, A transpose and
Yeah,
A transpose A are different.
they are different. Yes, yes.
So they are okay. So their eigenvalues are same, na? But they
Yeah, yeah, but the eigenvalues are same.
okay,
The
eigenvalues are
eigenvalues of
same,
A transpose are going to be same as eigenvalues of A transpose A.
but vectors are different.
Yeah, the eigenvectors are going to be different. Yes.
And sir, I have from the day one. Day one means from the when I was studying this week 5. Sir, I have a confusion to remembering this. A transpose A is Q1, and A transpose is Q1, and A transpose A is Q2. So is there any trick or something that
Okay, okay.
I,
There's going to
always
be a trick.
I
There's a trick.
confuse? Yeah.
There's a trick. Let me tell you.
Yeah.
So, yeah, here eigenvectors of A transpose and then A transpose A, right? This is out.
Ha ha
Okay.
ha ha.
A should be equals to what's this here? Q1 sigma Q2 transpose, right? Q1 sigma Q2 transpose. A is what M cross N, right?
Hmm.
A is M cross N. So obviously this should be M cross something,
Yeah, 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 yeah,
correct?
yeah, yeah.
So basically this is going to be M cross M. Okay,
Okay,
this is
okay.
going to be M cross M. And how do you get this M cross M? By doing this A transpose.
Got it, sir.
Okay.
Okay.
So basically this huh?
No, sir. Yes, continue.
Correct, right?
Yeah, yeah,
So
yeah.
by doing A transpose, you'll be getting M cross M, and then by doing A transpose, you'll get M cross M. So basically Q1 will be A transpose, and then Q2 will be A transpose A. Okay.
Okay, sir. Okay, got it, sir.
Yeah. So and then the sigma, right? In the sigma, you'll have the singular values, where the singular values are the eigenvalues of A transpose A or A transpose. Square root of the eigenvalues. Okay. Square root of lambda, where lambda is the eigenvalues of
So, sir, in exam, we need to solve all the things because it is too lengthy to solve. Or, sir,
no. You
say, only the eigenvalues are sufficient.
yeah. So basically, you can just look at the options. Okay. First of all, you will not be getting lengthy matrices.
Huh?
If at all this SPD problem is given, you can get 2 cross 2 matrix and at max 3 cross 3. Okay. Even if you
Oh,
are given 3 cross 3 also, it basically means the solution it's going to be kind of like easier only. Okay.
Okay. Got it.
So it's not going
And
to be difficult. Okay. It's too
In case if A is Hermitian, then will this singular value decomposition reduce to the original unitary decomposition?
Yeah. If A is Hermitian, right? Then
Yes.
basically this will be reduced to this UD U star form.
Okay. Thank you.
Yeah. Okay. Okay. So that's all we have from this from this
Uh,
session. Okay.
could you
Any
explain that
questions?
sigma matrix again, sir? Could you please explain that sigma matrix again?
Okay. Okay. Okay.
Sigma
One
part,
second.
yeah.
Yeah. Sure.
I'm unable to locate week 11 and 12 revision slides in this drive. Can you check once, Karthik?
Yeah. I will check that. Sure.
Is it there? Can you please check now once? Because I'm unable to locate it.
Okay,
Sir, you
sigma
have put it.
matrix.
Yeah.
Sigma matrix is going to continue square root of lambda 1, square root of lambda 2, square root of lambda 3, so like whatever non-singular eigenvalues you can get. Okay. Single, and then it's going to be 0. Okay. This is going to be the sigma matrix. Okay. And it's going to be of the size m cross n. Okay.
Okay.
Clear?
Yes.
Okay.
So the excess numbers are going to be zeros.
Yes.
When I
Yes.
say, yeah.
Yes. The excess numbers are going to be zeros.
Sir, can you provide the questions, the related topics
Yeah,
that we
the
discussed?
slides alone, yeah, we'll be providing.
So when it is tomorrow or
Which one?
no, sir? Not I am not talking about the slides. The question, the practice questions that you discuss in the slide, na, the topics.
Yeah. Those two it will be shared.
Okay, the practice.
The entire slides will be shared.
So where are you going to upload
Slides.
these slides, sir? Like,
Yeah.
will
More
it
Yeah,
be
important.
upload
Where
that
exactly?
in the supplementary contents will be providing. Okay, in the revision
no?
slides we'll upload.
One confusion is happening. I think Vishal is updating in some Google Drive, and then he's sharing that Google link, and most of us are missing that link. And then you are going to submit in supplementary content. Okay, that's fine. We will have to figure
Okay.
it out.
So what I'll be doing is I'll be updating it in this the Google Drive. Okay, and then I'll post on Discord also. Okay, mentioning
Uh,
that, providing the link and saying that it's updated. Is that okay?
So,
Yeah.
Actually, uploading in the revision slides portal
Yes.
is the better option. That's the best.
Yeah. That's the best option.
Guys, you can. I shared the link. You can check that link. It is Vishal sir shared that.
Rohit, but he has not uploaded his slide in that Google Drive. That's the problem. No? That's what he is saying.
Yes, I'm checking for week 11 and 12. It's not there.
Correct. And even Ram sir will also has not shared till now. Now he will share after some time. And then, sir,
Okay.
Ram sir,
Yes.
then the most important thing, right? Okay, thanks for taking us through all the 3 weeks and this video also. The most important thing is that, like, which all topics are important from examination point of view, and then what kind of questions we can expect, sir. We have, that if you can give some hint on that.
Okay, from the examination point of view, all I want you to understand is the how orthogonal matrix is. Okay, what is orthogonal matrix? What is a Hermitian matrix? And then the basic properties of Hermitian matrix, basic properties of this orthogonal matrix, and then the symmetric matrices. Okay, that alone, and then understand the nullity, the rank, the column space, and then the relationships between them. Okay, that alone, and if you're able to get this the end, the understand the end of the spectral theorem. Okay, spectral theorem as well as that SVD, right? SVD, that will be most probably sufficient enough. Okay, anyway in this also you should be knowing how to find eigenvectors, how to find eigenvalues. That is like basic, that's definitely needed.
So these are related to theoretical part, like some MSQ and all, right?
Yeah. So the problems part, the problems you'll be getting like few. Okay, I mean it won't be lengthy. Whatever you get, okay, whatever you're going to get, that's going to be solvable. Okay.
But anyhow, like, that linear regression and all, can be expected.
That linear regression and all, those lengthy problems you'll not be getting. Even if you get there, it will be like easier linear regression problems. Okay.
Sir, you
Sir,
are
it
saying
is.
both the things, sir. You might not get
Yes,
and
sir.
you will get
Correct.
same.
Correct.
So can you, sir, can you share the some practice questions related to the week 3, 4, 5, and SVD? Some practice questions, if it is possible, on the G
Okay,
drive.
okay. Yeah, we'll try. We'll try.
Just a clone of main exam, sir.
No,
Yeah,
not
yeah, yeah.
clone, not clone. Sir,
Yeah, we'll
Not the
try.
exact, obviously not the exact one. I'm asking the clone only, right? That's allowed.
Yes, sir. That's the right word. Huh?
Clone. Okay, you will not be getting the clone of the final exam. No, that you know. Okay. So,
and sir,
but
one more question, sir. Sir, the mock, I think it will be there by Wednesday or Tuesday.
it
The
will be
mock
there.
for end term.
Most probably by tomorrow will be released.
Okay.
Ah,
Also,
great. That will be
if we
better.
solve the mock, that it is okay to solve the mock.
What if you do not solve the mock? Is it okay? That's what you're
No,
asking.
if we
Yeah,
solve
yeah.
the mock, sir. If
If
we
we
solve
solve
the
the
mock, yeah.
if we solve the
May
mock, the
not be
similar
limited to
difficulty
that.
level and all the things are
No,
there in
okay.
the main.
No, no, no. It's not like if you're able to solve the mock, then that's great.
Uh,
Okay, but even if you're not able to solve right, it's all right. Okay, the level of difficulty it's not going to be same as the mock. Okay, it's going to be slightly lesser, I suppose. Okay,
okay. Sorry. Okay. It is
okay,
slider lesser than mock, slightly lesser.
yeah, yeah.
Okay.
Okay, okay then. So if you do not have any further